then check inside unhandled exception handler if stuff has been called or not, and if not, you're on a real environment. If it has been called actually your stuff, then you're in an antivirus emulator. But again, we get all this stuff for free from just executing the native bytecode. So I have a little bit demo of dirtbox itself. Oops. So I have a very simple test case in this case. Just some binary I wrote in assembler. Basically, what it does is called tick count and so on, but it doesn't really matter, as I will show you now what it does. So we just start execution, and I've got this debugger-like command line interface to it. And what you see here is, of course, first some debug output from the section object implementation. So we're loading some section objects for NT, DLL, and the image we're actually executing, creating these section objects. And then we'll be calling the loader initialize function to actually start execution. Well, this function expects 3 parameters, and well, we can just provide some value for them to work. So then we run into libcpu, start execution, and the first thing that will happen is a system call to NT open key. So the first thing at all that's some of the magic I've been telling you before, is that the NT DLL loader actually looks up a registry key, image file execution options, and then the file name of the binary you're looking at. And if this registry key is present, you can set certain options like debug flag, stuff like this, which is also very handy for malware analysis sometimes. But in our emulation environment, there's no such specific key there. So we're saying object name could not be resolved. And therefore we just give an error back from our system call, and NTDLL of course expect this, since usually there is no such key, and continues. Okay. So next thing is that it's invoking NT query virtual memory. So it tries to get some self-introspection into the address space that is currently executing, and determining parameters for relocation, stuff like this. And the funny thing is, NTDLL contains a lot of debug strings, debug output, and these are even there in the release builds, but they're disabled by a certain byte, a static byte. And if you just patch this byte to instead from 0 to being any non-zero value, it will output all these debug strings for you. So actually, these debug strings here are not created by me, but they're created by the original NTDLL code, which is very useful for debugging my stuff. So, okay, we don't provide a proper process ID, but yeah, of course we could fix that. There's some random debug output. As you can obviously see, this environment is not 100% accurate either, but that's easy things to fix. So next thing is it invokes NT-OpenKey event. This is like just management stuff it needs for using critical sections later on. It's very nice if you find very little information on these special keyed events and stuff like this, but it's a very performant implementation for handling critical sections and in case there's no memory, so you don't screw up with like throwing exceptions and so on. It then calls NT query system information to get various information about the currently running system, like the size of a page in bytes, stuff like this. And what you see here is calls to NT allocate virtual memory. So, well, this is either already the setting up of the heap or the NTDLL creating space for some data structures. And this goes on for some stuff, so you have some more initialization of memory and so on. And the next interesting thing is NT open directory object, where the directory objects are just virtual directories in the kernel's namespace, object namespace. And there's a directory called known DLLs. And this known DLLs thing is basically to both save memory and speed process startup up. So these known DLLs, there's like these DLLs you really see in almost every process, like kernel 32 DLL, user 32 DLL, and so on. And these DLLs, they're actually not mapped for each process at each startup, but instead they will be mapped at system boot time, and yeah, then you just can map the existing section objects into your process. And this has a very nice side effect if you actually care about exploitation. It means that known DLLs are always at the same address. So even with address space layout randomization enabled, you will always have them at a fixed address. So imagine, for example, a scenario where like you have a vulnerability in some program, that is an information leak, but it will also crash the process. But anyway, if you can somehow restart the process, you can try a second time, because the addresses you leaked from these known DLLs will still be valid, even though ASLR is enabled. So, or if you have like two different processes and you have an information leak vulnerability in the one, and you have a exploitable buffer overflow or whatever in the other one, then the addresses from the one process, at least for known DLLs, will be valid for the other process too. So that's very nice way to circumvent ASLR if you have an information leak vulnerability somehow. Well, of course, that's not the reason why Microsoft implemented it, I guess. But instead, yeah, you save memory because you don't map these images a lot of times, and of course, process startup is faster. And then they will query a symbolic link object, which is the known DLL path. So this whole known DLL stuff is restricted to libraries lying in this certain directory there, so that malware cannot, I don't know, inject its own DLLs or whatever. And then we get some nice debug output actually from NT-DLL new process, image pairs is this, and so on, current directory is that, and the search path is this. And then it actually calls NT-open-file on the directory where it thinks it's the image is lying in, is residing in. So the reason it does this is it actually queries volume information about the volume, which is kind of the disk device or whatever this specific binary is in. And it does that to find out, is this actually a removable media or is it a fixed media? So if you like have execute binaries from a USB stick, it has some safety precautions in case you would just remove the USB stick and whatever. There's some PE flags like only on fixed media and stuff like this too. So that's just for finding out if you're on a removable device or network device for that matter. And does some more memory allocation and so on. Then it calls a different system call to find out the same information again. And you know, this system call here, system and TFS call. Well, no, this is the first one of those, but yeah, this is to find out if it's actually mounted or not. And then later on, it will do the same thing again with a different system call. So actually in Windows, there's different system calls doing the same stuff, or at least providing overlapping information. Then it tries to access a file, which is an image file name .local. I didn't really investigate what this is. I don't know, maybe somebody else can tell me after this presentation what these .local files are, but it doesn't need these files. Usually you don't have .local files, right? So if it's not there, then it just continues. So we kind of find that file, but yeah, let's continue. So it now calls NT open section on kernel 32 DLL because kernel 32 DLL is one of these known DLLs. We don't need to actually read it from the disk and map it into the memory, but it's already in the memory. We just need to add it to the current address space by ntmap open section and then ntmap vo of section. So that basically loads kernel 32 DLL, and we can say successful PE loading and this base address and so on. So let's continue. Okay, so NT-DLL gives us the debug output. It's loader load DLL is being called, and we're loading kernel 32 DLL from nowhere because it's a known DLL. Maybe there should be some path there, but yeah, maybe not providing enough information. So it opens the section kernel 32 DLL again. No, sorry, I'm screwing up here. So it's now saying loader NT-DLL. DLL is used by kernel 32 DLL, so this is where it starts resolving the dependencies of the different files. So it starts snapping imports, basically resolving imports from kernel 32 for kernel 32 DLL, imports from NT-DLL. And what it of course has to do is, well, these import sections are usually not mapped writable, so it maps them writable. We'll modify the stuff that are putting the addresses of the imports there and then map them non-writable again. And then it works a very funny system call NT-flush instruction cache, which is a no operation system call on the x86 architecture. But you know, there's different architectures that actually require that cache instructions that require you to do some hardware stuff to flush this instruction cache, like for example ARM. And the system call then flushes these instructions because actually these import tables are usually not only tables of addresses, but instead the compiler will generate jump instructions there, so we have to do this. But it does nothing on the x86 architecture. So then there's some more initialization of the loader, and then here we see that the DLL entry points are going to be called. So it's calling some init routines here, and TDLL has a very, very short init routine itself. That's not very interesting. And then it starts the kernel 32 init routine, which will do a lot of the process environment setup. So kernel 32, it again calls anti-query information process to find out some information about the environment and so on. And in this case, it also asks for the process cookie. So the process cookie is that thing that is used for the heap cookies, for example. It's a random value provided by the operating system through the system call. And well, then it collects some more information and then creates a new section, which is just some memory area it will use for local procedure call communication with the Windows API port. And the Windows API port is part of the common subsystem on Windows. So it as CSRSS exit process. So this stuff does some tracking of processes. It does terminal windows for you, stuff like this, the console windows, I mean. And then it starts communicating with this. So it queries this object a little bit and does some stuff we don't need really to implement because it doesn't really care about return values. It allocates some more memory, and then actually it calls out by NT request wait rep reports to that local procedure call. So it actually starts communicating with CSRSSX, saying, hello, I'm a new process, and if it's actually a console command line PE binary, it will ask the CSRSS exit to create a new console window for you. So all these console windows from your command line processes, they're actually belonging to the CSRSS process instead of belonging actually to yourself. And then it calls anti-resistor thread terminate port, which means the port will be closed as soon as this thread exits because it's the main thread. But again, I didn't get to implement all these LPC stuff yet. And then, it queries some more information again. Kernel 32 also parses these image file execution objects, but again, we don't have the specific key here. And then it does some mapping of the NLS sections. This is natural language support. So there's a lot of preloaded stuff for supporting different locales and all processes, and in this case I just took the original Windows files too and mapped them on demand there. So it maps these files like Unicode NLS into the process and so on. And then it does anti-query default locale, which is a very obvious thing, but I didn't get to implement that either. Doesn't really need that anyway. And then it starts loading more of these files, locale NLS and sort key NLS and whatever Microsoft uses all these files for. I mean, the benefit of executing all the bytecode is, I mean, it obviously needs those files, but we don't even need to care what it needs these files for because, well, the bytecode that handles this file is there anyway. Then it queries this section and gets some information about these. Then it loads sort tables, some more stuff. And now we're getting to the interesting part because now it allocates some more memory. That's just heap stuff. And then it requests some more CSRSS stuff and waits for the reply. And the problem here is that the whole LPC stuff and the whole CSR implementation stuff is entirely undocumented. So I'll have to reverse CSRSS actually a little bit too. And I didn't get to the part to do all this until now. So as I've said, it's like a Sisyphus tale. But again, for this case, if you just provided some empty return data, it doesn't really complain and care. So, I mean, of course, this adds to detectability, but you don't really need to implement all this stuff. And then we're getting to a funny thing where I'm currently stuck. It actually, the loader, it tries to find one specific address-based query module data, which is there in the kernel 32 DLL I'm using, but it's not finding it, and I didn't debug why it doesn't find it yet. So from here on now, it will fail. It says, okay, I couldn't find this specific API, and then kernel 32 starts to act up, and it says I need this, and so on, and then it basically starts raising errors, and that's as far as I've got. So I didn't even get to the actual original entry point of the binaries yet, because it's so much stuff to implement, but I'm like, this is the last thing that the kernel 32 initialization routine does, so I'm almost there, so to speak. And yeah, I mean, for help of debugging, I have some nice stuff built in here. Actually, it's breakpoint support too, and this is actually what has happened till now. So this memory area here and these memory here and this memory here is what we initially provided, but all the memory here has been allocated by heap stuff or different other stuff, and then kernel 32 DLL has been loaded